In this second video on sampling distributions, I'm going to be talking briefly about the sampling distribution of the sample mean x bar, and specifically actually the central limit theorem. And by the way, when we talk about the distribution of any variable, specifically there are two things that we're interested in learning about. First is, what's the shape of that distribution? If you're interested in talking about the distribution of stock returns, of earnings per share of firms, of the birth weight of babies, etc., how is it shaped when you construct frequency distribution? And secondly, what are the parameters of that distribution? For example, the mean and the standard deviation. Now, obviously, the greatest, if I may put it that way, of the distributions that you would have learned so far would be the normal distribution. The elegance of it lies in perhaps two, well, maybe three key attributes. First is it's a symmetric distribution. So we know that if you were to split this into two, one side is going to be a mirror image of the other side, and the center of the distribution, as you see here, is the mean. However, the applications of this distribution is what makes it quite so excellence in all aspects, really. The first is, before the facts, we know that approximately 68% of the observations are going to lie within plus or minus standard deviation of the mean. About 95.5% would lie within plus or minus 2 standard deviations of the mean, etc. Secondly is that we can fully characterize such a distribution simply by knowing the mean and the standard deviation, or if you like, the mean and the variance. Variance would be the square of the standard deviation of the distribution. We need not know any other parameters to be able to fully characterize that distribution. And thirdly, we can easily calculate probabilities associated with possible values of that variable before the fact, once we are armed with information regarding the mean and the standard deviation. Anyways, so as you can see, if we determine that the distribution of the sample mean has the same shape, that would be wonderful, because our lives will be made a lot easier in terms of the types of inferences that we can make. Now though, there are two cases within which to examine the distribution of the sample mean. First is if the underlying population has a normal distribution. If that's the case, then theory shows, and actually evidence confirms, that in repeated samples from such a normal population, that the distribution of the sample mean x bar will also follow the normal distribution, and it doesn't matter what the sample size is. And even more importantly, as the sample size with which you are working increases, you can find that the sampling distribution will become increasingly tighter around the mean, as you can see in this illustration as you move up from lower samples to higher samples. So this has an important implication in empirical applications. As you can see, the larger the sample size that you work with, the tighter the distribution would be, and therefore any sample mean that you calculate from your sample would be one that is as close as possible to the mean of the underlying population, which would be quite wonderful, because remember, you're going to be using your sample mean x bar to make inference on the population mean. So the closer, the tighter the distribution is, the better your sample mean will approximate the underlying population mean. And generally, at least from a classroom standpoint, it's always advisable to ensure that your sample size is no less than 30. Now though, in that, the parameters of the distribution would be as follows. The mean of the sample mean would be the population mean, and the standard deviation would be so defined, which is the population standard deviation divided by the square root of your sample size. So again, in talking about distributions, two things. One is the shape of the distribution, and we have ascertained that if the population is normal, the distribution of x bar would also be normal. Second would be the parameters of that distribution, and we have now confirmed that the mean of x bar, which is what you see right here, the mean of x bar would be the center, the population mean, and the standard deviation, which determines the tightness of the distribution, is the ratio of the population standard deviation and the square root of the sample size. And armed with this information, we can actually calculate probabilities associated with possible values of x bar, as I'm going to show in the next video. But to do so, we're going to be calculating z, and as you can see here, the denominator is going to be the standard error, aka the standard deviation of x bar, right? Compared to the z statistic we calculated in the past when determining probabilities associated with the random variable x. So as you can see here, right up here, this is for the random variable x, such as earnings per share. And this is for the random variable, the sample mean earnings per share. There you go. Now, case number 2. What if the population is not normal? Well, in this respect, we appeal to the Central Limit Theorem, which argues that with sufficiently large samples, that the sampling distribution of the sample mean will still be normal, at least approximately, with the same population mean and same standard error. And therefore, what this is telling us is that it doesn't matter how the underlying population is shaped. It could be normal, it could be in any old funky kind of shape, as you see out here. As you increase the sample size, as you can see here, the sampling distribution becomes increasingly normal, with the mean of which would be the population mean either way, and the standard error, which is the standard deviation of x bar, would be as already pointed out right here. And that's all there is to it.